So there are three main aspects that we have been looking at in this course. The first aspect was the real world is mostly continuous. How do we take these continuous signals and convert them into discrete signals so that we can do some processing on that? That was one big piece of our course. The second big piece was, well, if you're taking these signals, how do you understand using digital systems what kind of frequencies are present in those signals? Or how do you process them using DFT? And the third major piece is that if you are designing a digital system, we have filters inside those digital systems, and how do we understand the design of those digital filters? And when I say design, of course, in previous homeworks and examples, you have always done, okay, the filter I need is a low pass filter. So you always have a sense of what kind of filter you want, but design, the term that we are using here, is actually saying that filters that can be implemented in a digital system. So that is exactly what the design means, that you will have a rough idea of what you want with your filter, but now you want to convert that rough idea into a formal implementation that you can use MATLAB or Arduino or Raspberry Pi or any other digital system to really process your signal. Okay. So, and the reason for that is, when I say they can be implemented, let me remind you that so far we have talked about ideal filters, but ideal filters cannot always be implemented. So let's take the example, you figure out that whatever you were working with, at the end of the day, when you digitize things, and I'm not going to talk about the continuous aspects of this block diagram because the assumption is you know all of those things. So at the end of the day, you realize that you need a filter, AHN, which is an ideal low-pass filter. So what is an ideal low-pass filter? Well, it has a discrete time Fourier transform, which is given by 1 for absolute value of omega less than or equal to some cutoff frequency omega c, right? Let's say pi by 4, and it's 0 for omega c less than or equal to omega less than or equal to pi, and of course then it periodically repeats itself. Okay. By the way, let me remind you that one of the common things I see in exams is that students write 0 otherwise, and that is incorrect because a discrete time Fourier transform is not 0 after omega c. Okay, so just be careful about that. Okay, so if this is my ideal low pass filter, then you say, well, I know how to compute the inverse DFT of that, and I will get this formula, sine of omega Cn over pi n. So this is an ideal filter, but what is the trouble with this filter? That n in this expression goes from minus infinity to infinity. So how do you really implement it inside a digital system? You can't ask MATLAB to do the convolution sum from n equal to minus infinity to infinity, or 0 to infinity for that matter. Right? You can't have infinite, you cannot have infinite sums computed inside digital systems. You also cannot use the DFT-based approach that we talked about earlier, because this is not a finite duration sequence. So when we talk about design, what we are really saying is, how do we use a filter that can be implemented inside a digital system? So how do we implement a filter, let's call it H tilde n, inside a digital system? So H tilde n, we'll come to that later, what it means. It can be implemented, but one of the key requirements when we are talking about then design is that H tilde n has a Fourier transform. So H tilde n has a Fourier transform H tilde of e to the j omega, such that the Fourier transform of the filter that I implement is very close to the filter that I really wanted. That is ideal, but I cannot get to it. So such that H tilde E of j omega is close to the ideal H of e to the j omega filter. So that is what we are going to study. How do we start with a design specification and convert it into something that can be really implemented? Okay. So there are two main ways in which we can achieve this objective of designing an implementable filter. And the first, so there are two solutions. The first solution is very simple, which is that we approximate the ideal filter by a finite impulse response filter, or FIR filter. So let's look at what is an FIR filter. An FIR filter is one whose impulse response is 0 for all n less than n1 and n greater than n2. So an FIR filter is a filter, as the name implies. It has a finite impulse response, and finite in the sense that it is only non-zero for a range of values of n. It becomes 0 after a certain value of n, and it stays 0 after that. Okay. So an FIR filter effectively is described by a finite number of values that you need to store inside a digital system. Now, of course, we are interested always in causal systems. Causal filters, the definition of which you saw in your earlier class, is that the output of the system does not depend on future input. Now, a necessary and sufficient condition for a filter to be causal. So necessary, sufficient condition for a filter to be causal, so the condition is that Hn has to be equal to 0 for all n less than 0. So you don't want to generate an output before the input has been applied, which is applied at n equal to 0. So the first then solution of generating an approximation to an ideal filter is by approximating a filter with an a causal. So we use a causal FIR filter, and the definition of which is that Hn will be equal to 0 for all n less than 0 and Hn equal to 0 for all n bigger than some other number, n2. N2 could be 1,000, 10,000, 50,000, but after that the response will stay 0. Okay, so let's just replace n2 by capital N, just a number, and or n minus 1, and then this will be called a length n FIR filter. So often people will say I have a length 256 FIR filter, which means that the impulse response of the filter is 0 beyond n equal to 255. Okay. Now, why do we believe that a causal FIR filter can be implemented inside a digital system? The reason is, so implementation wise, you first have to store only capital N numbers. So if you have a length 256 filter, you have to store 256 numbers. So that's easy. And secondly, convolution can be directly computed. So why is that? Well, your output Yn is Hn convolved with the input. Right? So then we write the formula n from minus infinity to infinity, h of m, x of n minus m. But my h is only non-zero for m from 0 to n minus 1. So I can write this as m from 0 to n minus 1, h of m, x of n minus m. So this is a finite sum. So for every value of n, you can generate this by doing simply n multiplications and n minus 1 additions. So implementing an FIR filter in digital systems is pretty easy. You just use the direct convolution formula with the limits replaced. So this is simply equal to h0 x of n plus h1 x of n minus 1 and so forth, plus h of n minus 1 x of n minus 1. So you store h0, h1 up to hn minus 1 in your system. Every time a new input comes in, you simply multiply these numbers with the inputs and past inputs, you generate an output. Yeah. Now the second way of approximating an ideal filter is to approximate it. So approximate an ideal filter by an infinite impulse response filter or IIR filter that can be described by a difference equation. Now, this may sound counterintuitive because we started with the aspect that an ideal filter has an impulse response which typically goes from n from minus infinity to infinity or 0 to infinity. So you cannot use the convolution formula directly. But the solution to that I am saying is you start with the ideal filter and then replace it with another infinite impulse response filter. Right? And if you, so what is an infinite impulse response filter, especially if we talk about a causal IIR filter? That is, of course, Hn equal to 0 for all n less than 0, but Hn does not stay 0 beyond any value of n. So it keeps on going. So of course then you cannot use the convolution formula directly, and that's where this additional distinction comes into play. An IIR filter that can be described by a difference equation. That is the key. Just because a filter is an IIR filter does not mean it cannot be implemented. It can be implemented as long as it can be described by a constant coefficient difference equation. So two examples. One example we already saw. Example 1 is Hn equal to sine of omega Cn over pi n. Clearly this filter, no matter what value of n you put in, it doesn't stay 0. The impulse response doesn't stay 0, so this is an IIR filter. I could even limit for n equal to, if it's 0 for n less than 0, it will still be an IIR filter. Example 2 is Hn equal to AN UN. Okay. For example, I could say it's 0.5 to the n UN. So of course, since it is starting at n equal to 0, this is causal. And you can put in any value of little n, it doesn't stay 0, so this is IIR. Now, one of these filters satisfies this constraint that it can be described by a difference equation and the other does not. So the first one, this filter cannot be described by a difference equation, and the second one we'll see can be described. And so this one cannot be implemented. The first one cannot be implemented in a digital system. The second one can be. So instead of telling you why it can be described by a difference equation, I'll go the other way around. I'll say a system is described by the output is given by yn equal to the current input xn plus 0.5 y of n minus 1. Okay. Now this is a difference equation, and all of you have done many examples of how do you find the impulse response of a system that's given by a difference equation. So what is the impulse response of this system? It's of course easy to see. You can verify that it is indeed a linear system. It's a time invariant system. So those properties apply. Then the question is, what is the impulse response? So we take the Z transform of the left-hand side, that's Yn, and we take the Z transform of the right-hand side, and then we use the properties of the Z transform. So let's call the Z transform of the sequence Yn as Y of Z, and the Z transform of the sequence Xn as X of Z. So Z transform of Yn is simply Y of Z. Now Z transform is linear, so I can take the individual Z transforms of each term. So the first term Z transform is X of Z, plus I'm looking at the Z transform of 0.5 Y of n minus 1. Again, I use the linearity property, so that is simply 0.5 Z transform of Y of n minus 1. And then I use the most frequently used property of the Z transform. So there is this very important property of the Z transform, that a delay in time. So if you are given Y of n minus n naught, if you delay your sequence by n naught, that is simply equal to Z to the minus n naught Y of Z. Okay. So this means that the Z transform of this is 0.5 Z to the minus 1 Y of Z. Okay. So if I collect then these facts together, I get Y of Z. I bring this term to the left hand side, 1 minus 0.5 Z inverse equal to X of Z. Okay. And now I remind ourselves of the convolution property of the Z transform. So if you convolve two sequences Yn, Xn, the Z transform of that is equal to Xz, Yz, or let me put it H. So if you convolve two sequences Hn, Xn, then the Z transform of that is Hz, Xz, which is convolution in time is multiplication in the Z domain, right? So we know that Yn equal to Hn convolved with Xn, and the Z transform of that means is Y of Z equal to H of Z, X of Z. So our goal is to find the Z transform of my impulse response Hn. So that is simply equal to H of Z equal to Y of Z, X of Z. So I basically bring X of Z to the other side, cross multiply, and I get 1 over 1 minus 0.5 Z inverse, and this is effectively H of Z. 1 minus 0.5 Z inverse. Now I have found the Z transform of my impulse response. So to find my impulse response, all I have to do is find the inverse Z transform of this Z transform, and that will give me my impulse response, Hn. Right? So Hn is simply equal to the inverse Z transform of 1 over 1 minus 0.5 Z inverse. So to find the inverse Z transform, it's not just enough for us to have this, we also need the region of convergence, or ROC. Okay. Now there are two ROCs that can be associated with this sequence. One ROC is that absolute value of Z is bigger than 0.5, and the other ROC is that absolute value of Z is less than 0.5. Okay. So depending upon that, you get two different answers. If you remember your Z transform pairs, then the inverse Z transform of this setting is either 0.5 to the n u of n, or it is minus 0.5 to the n u of minus n minus 1. Okay. And that will be determined by which region of convergence you are in. So the first region of convergence goes with the first sequence, and the second region of convergence goes with the second sequence. Okay. And if you so we will of course go with this first region of convergence, because if you look at HN, if you remember your definition of causal systems, this is the first one is a causal system. The second one is not a causal system. Right? The second one is going from minus infinity up to 1. The first one is going from 0 to infinity. So this is a causal IIR filter, and we'll go with that one. Okay. So the point of all this exercise was that we end up with an impulse response. So this difference equation, what we did was we found that this difference equation corresponds to an LTI system whose impulse response is this 0.5 to the n un, which means that if you flip it around, this IIR filter, this causal IIR filter, can be expressed, even though it is an IIR filter, it can be expressed as a difference equation. Okay? And if it can be expressed as a difference equation, then it is really simple to implement, because all you have to do in your digital system is have a circular buffer which keeps track of the previous output, and then every new time instant it just shifts, makes your current output your previous output, and then multiplies it with 0.5 and adds it to your current input. So writing this code is really simple. Even though your impulse response is infinite, you can implement that because it is given in terms of a difference equation. You're not going to use the convolution formula, but you can implement it in terms of a difference equation. So the general question we can ask is, then this was a special case, right? So the question is, when does an LTI system result in its description being given by a difference equation? So I give you an impulse response. So let's say I give you a frequency response. You find out that this is the frequency response I'm interested in. From that frequency response, you compute the impulse response. So you start with, this is your desired frequency response. You go from that to your impulse response. How do you know whether this system, and you compute HN, and in almost all the cases, this HN will be an infinite impulse response system. How do you know that this system can be implemented in a digital system? Well, you have to verify that it can be expressed as a difference equation, a constant coefficient difference equation. So how do you verify that? Well, the test is very easy. You take the Z transform of this impulse response. And the answer is that whenever the Z transform of the impulse response Hn can be expressed as a rational function of two polynomials in Z inverse. Anytime you can do that, you are guaranteed that your system can be expressed as a difference equation. So h of z should be, we should be able to write h of z as a fraction, as a rational function of two polynomials in Z inverse, pz over qz, where the numerator polynomial is a degree m polynomial, and the denominator polynomial is a degree n polynomial. Why should that be true? Well, remember that h of z in the Z domain for an LTI system is, this is equal to y of z over x of z. So you are saying y of z over x of z is this fraction. So you cross multiply, right? So this means that if you cross multiply, you get y of z times q0 plus q1 z inverse plus qn z to the minus n, that is equal to x of z p0 plus p1 z inverse plus pm z to the minus m. Right? And now if I take the inverse Z transform, then I just take the inverse properties, right? So the inverse Z transform of Q0 YZ is simply Q0 YN plus the inverse Z transform of Q1 Z inverse YZ. We know Z to the negative some power is nothing but a shift in time. So that is Q1 y of n minus 1. And we keep on going, and that's Qn y of n minus capital N. That is equal to P0 x of n. I do the same trick. P1 x of n minus 1 plus P of m x of n minus m. Okay, after taking the Z transform of this earlier equation. So indeed, if the bottom line is that if my impulse response has a Z transform which can be written as a rational function of two polynomials, then I am guaranteed that my system can be expressed as a difference equation. The difference equation is then given by, this is the constant coefficient difference equation. Constant coefficient because all the coefficients of these difference equations are constant. And implementation of this in hardware is really simple, because all you have to do is have two circular buffers which keep track of up to n passed outputs and up to m passed inputs. And then you just do this simple equation. right? So you can write your yn. Of course, I can take it on the other side. I can write my yn equal to p0 xn plus p1 x of n minus 1 plus pm x of n minus m, and then I take the other quantities here, so it's q1 y of n minus 1, keep on going, minus qn y of n minus capital N divided by q0. That's my yn. So what this is saying is, every time a new input comes in, I simply compute the sum, which is a finite sum, and assign that to the output. So implementation is really simple. So the bottom line is that a constant coefficient difference equation, if you are dealing with an IIR filter or a finite impulse response, these are two of the ways that we can implement digital systems. And so the design of digital filters effectively boils down to approximating the ideal filter or an ideal filter by either and we are always going to work with a causal FIR filter, in which case we just use the direct convolution sum, or an IIR filter that can be expressed as a constant coefficient difference equation. And the test is what we talked about for AHN. And in both cases, of course, in the IIR case, it's easy to see because we are directly using the test being that we take the impulse response, compute its Z transform, and the Z transform must have this rational form. But even for the FIR filter, as we will see, in both these cases, Z transform plays a very important role for understanding the behavior of filters. So we'll talk about a few things that will remind us of the Z transform. So quick review of the Z transform. So a Z transform is defined for a discrete time signal or discrete time sequence. Is given in variable Z, where Z is a complex number. So the formula of Z transform is, if you want to compute the Z transform of a sequence, that is n from minus infinity to infinity, G of n, Z of minus n. Okay. Now this is an infinite sum. So Z transform, whenever you get an expression, it's not just given by an expression in Z or Z inverse. It is also, there is also associated with it what's called the region of convergence, or ROC. And as the name implies, this is the region of the complex plane for which the infinite sequence, infinite sum converges. And convergence means that if I compute the absolute value of g of z, that should be less than infinity. Okay, so region of convergence is defined as the values of z for which absolute value of g of z is less than infinity, for which it is defined. And the region of convergence is always talking about, since z is a complex number, you are talking about this two-dimensional complex plane. So you are looking at which part of this z plane your g of z converges. And now complex number, we go to the polar form. So the complex number z in polar form is given by r e to the j theta. Okay. And it turns out, we won't go into the details of that. You should have seen that earlier, but the ROC depends only on the absolute value of z and not on anything else, which means that, so absolute value of z is simply equal to r. So this means that ROC depends only on the distance from the origin, which means that if your g of z converges, let's say at this point, so this is the point where your g of z converges. Let's call this is about, say, r is equal to 2 here. Well, if it converges at this point, it doesn't matter if your z is on any point away from the origin for r equal to 2, it will remain convergent because it only depends upon the distance from the origin. Okay, angle does not play a role in the convergence of the z transform. So because of that, the region of convergence is always an annulus region. What this means is there are only 3 types of region of convergence that are allowed that will make sense. One form is that you say, here is a circle and your z transform converges for all values outside this circle. Okay. So this circle could have radius 1, 2, or whatever. Right? So that's why you say, well, the region of convergence is defined as absolute value of z bigger than, let's say, some number a. The other case could be that the region of convergence includes everything inside a circle. Okay. So the region of convergence in that case is given by absolute value of z is less than a some number. Or the third case could be that the region of convergence is the area, it's the donut shaped, it's the area between 2 circles. Okay. So in that case, your region of convergence is given by A1, between A1 and A2. But the region of convergence always has this annulus form because the convergence is a function of only how far away from the origin and not the direction. Okay? So you cannot have a region of convergence This is not a valid region of convergence. You can't have a region of convergence which is like this. Okay? You can't say this is my region of convergence. Why? Because if this point is, if at the top you have convergence, then all points which are that far away should be converging also, because it's a function of how far away you are from origin. So let's find out what is the relationship, and that is a very important thing to find out, because eventually we want to understand the role of Z transform, poles and zeros in the frequency response of an LTI system. So for that, we have to understand what is the relationship between Z transform and the DTFT. Okay. So remember again that G of Z is n from minus infinity to infinity, G of n e to the minus Z to the minus n, where Z is a complex number. Now let's talk about the Fourier transform of the sequence. The definition of that is n from minus infinity to infinity, G of n e to the minus j omega n. What do we see here? That the Fourier transform G of e to the j omega is nothing but the Z transform evaluated at e to the j omega. If you replace the Z transform, you replace Z with e to the j omega, you get back the Fourier transform. Now remember, Z is a complex number, so I wrote it earlier, Z can be written in polar form as e to the j theta, or r e to the j omega, where omega is a number between minus pi and pi, right? It tells you which direction you are, and r is the radius. So if you are in this big plane, this two-dimensional plane, what is this relationship telling you? That the discrete time Fourier transform corresponds to the Z transform evaluated at a distance of 1 from the origin. Okay. So Z equal to e to the j omega, as omega goes from minus pi to pi or 0 to 2 pi, whichever convention you want to use for your direction. This makes up a circle with radius 1, or this is called unit circle. So in the Z plane, right, Z transform it has a variable which is a two-dimensional variable. So if you have to look at it inside, if you have to visualize it, it's basically a two-dimensional plot, right? It's a surface on a two-dimensional plot where the variables are given in this 2D and the values are coming out of this page, right? So the Fourier transform is the Z transform evaluated on this unit circle, where the distance is 1 and each, so for example, this point on the Z transform is effectively your G of e to the j0, right? This point on the unit circle is effectively G of e to the j pi by 2. So as you go from here to here, you are going from 0 frequency to pi frequency. As you go from here to here, you are going from 0 frequency to minus pi frequency. Okay. So dTft is equal to Z transform on the unit circle. And of course, as we talked about earlier, sometimes your Z transform exists, but your discrete time Fourier transform doesn't exist. So what's the definition of discrete time Fourier transform existing? Of course, it's the same definition that g of e to the j omega should be less than infinity. So you can tie the existence of discrete time Fourier transform to the region of convergence of your Z transform. So existence of dTft requires that the region of convergence, so it requires that the region of convergence contains the unit circle. So the conclusion that we can draw from this are, number one, we can have the Z transform, but the dTft may not exist. Okay. So that is why it's said it's just like the relationship between Laplace transform and continuous time Fourier transform. Okay. If you remember, continuous time Fourier transform may not exist, but Laplace transform almost always exists. Okay. So it's the same relationship. Z transform almost always exists, but dTft may not exist. Now, when will the dTft exist? If the unit circle is part of the region of convergence, then dTft exists. Okay. If the unit circle is not part of the region of convergence, then the dTft does not exist. Or at least the dTft does not exist in the absolute value sense. There are some cases where we can make use of, for periodic signals, we can make use of the discrete Fourier series. That's a different trick. But if we stay with the usual definition of the discrete time Fourier transform, if the unit circle is not part of the region of convergence, then the dTft would not exist. So if you think of it, the Z transform, and your book has nice illustrative pictures for that. The Z transform is basically a surface on this two-dimensional complex plane, right? And your Fourier transform is effectively whatever are the values of that surface on that unit circle. It's like you take that unit circle and then you flatten it and you get back your Fourier transform.